In this experiment, I'm going to be demonstrating how analog to digital and digital to analog converters work. But more importantly, what I'm really after is a test bed that will allow me to show how various units like the Rigol up there, which is a mixed signal oscilloscope, work. And to do that, I set this experiment up. It's one of the experiments from the modern electronic communications laboratory notebook. But the basic reason for doing this is so I'll have a test bed for the MSO and also for the analog discovery. But before I go down that line, I thought I might also show you a few other historical items that are in the same vein. In other words, ways to test digital logic that have evolved over the years. In the early days of digital logic, resistor transistor logic and later TTL, and here we're talking 60s, the tool of choice came to be a logic probe. This is one of the logic probes. And the nice thing about the logic probe was that it helped resolve the issue of zeros and ones. In other words, instead of having to use an oscilloscope and interpret it, you could kind of move down the line on an IC looking at the outputs and quickly determine if they were a 0, a 1, and then later better ones could show you if they were moving, in other words, if it was toggling and so on. Well, it didn't take long for people using these devices to realize that what they really wanted was something that would let them examine all the IC pins at once. So this is a device that was brought out. This is a 16-pin logic monitor. And you would just clip this over the dip. So for example, if you had a board like this, this would simply go over the IC like that, and then you could monitor the values from the top on LEDs. This particular one actually will even figure out which pin is VCC and which pin is ground. That is, it finds the most positive voltage and the most negative voltage on the IC and uses those to power its internal logic, and then it displays the rest of the signals based on that power and ground. Well, as TTL began to be replaced by CMOS, another device came out, which is represented by this device, and as you can see, it can switch between resistor transistor logic, diode transistor logic, transistor transistor logic, and CMOS. And it had its own power supply, and so it had a plug that you would plug in, but you also had a cable that you used to attach to the VCC and ground of the circuit you were working on, and you did that so that the device would know what the high and low levels were that it was trying to operate from. And then, of course, you had a logic monitor that would once again clip on top. As ICs grew in size, they quickly outgrew the 16-pin format and went to 18, 20, 24-pin, and so on. Eventually, a series of test clips were developed, like the ones you see in this box, that would go everywhere from 14 pins all the way up to 40 pin. This would be the form factor for that kind of clip. And once again, you would clip it on, and then on the other side, you had test point connections where you could clip a scope or touch a logic probe. It wasn't long until DIP began to be too bulky, and so chip designers began looking for other packaging techniques, and one of them was the small outline integrated circuit, or SOIC. And so it wasn't long until kits like this came out, which were intended to do the same thing, but on an SOIC form factor. This, for example, is a 16-pin SOIC socket, and to give you an idea of the approximate size of that relative, this is a dip socket for the same 16 pins. So you see it was about half the size. So by the time this clip set had come out, a lot of boards were going to SOIC. Not long after that, surface mount began to be popular. And frankly, at that point, it got to be almost impossible to find good test connectors, because surface mount, as I'm sure if you've ever worked with it, you know, it mounts right to the board, so flat that there is no place for these clips to find any purchase. So with surface mount, this whole process of testing went out the window. And today, automated testers can test surface mount, but frankly, except for that, you're back to using an oscilloscope probe and hoping you don't short a couple of pins together and blow the whole circuit. So now I'm going to set up to show you the A2D and D2A, but before I do, let me just briefly show you what this circuit is. It consists of an analog devices 670 A2D converter. The input is applied on the left. A clock signal is applied at this point, and at this point it's a 10 kilohertz clock. We'll change that a little later. The output of the A2D converter is being latched in a 374 using the clock signal, and then that is being fed to an AD 557. Once again, the AD stands for analog devices, and in this case it's a D2A converter. It converts that digital to an analog signal at this point where this oscilloscope test probe is located. Now right now I have this power supply set to the input, and as I vary the input up to about, I have it set up to go to about 2.5 volts full scale. Over here you see on the oscilloscope at the top is the clock signal. The bottom trace is the D2A output. So let me try to hold this as I lower the D2A input, or the A to D input, and you watch the output go back to 0, as you see there. So in other words, what this circuit is basically doing is simply converting an analog signal to digital, latching the digital value, the 8 bits, then reconverting those 8 bits back to an analog signal. And of course, if all you were trying to do is just measure a single voltage, there's a lot better ways to do that than this. And in fact, A to D converters and D to A converters have largely become obsolete in the chip form. The reason is that, for example, in Arduino, this is an 8-bit system. An Arduino, I think, offers a 10-bit or 12-bit A to D converter on board, and it has an A to D converter for each input. So for example, an Uno, I think, has 6 or 8 analog inputs, each of which has its own A to D converter, its own internal logic, and it can convert digital back to analog and put that out on the same pin if you switch the mode from input to output. So basically everything that you see here is now inside an Arduino several times over, and an Arduino costs about the same as this chip. So obviously this is not an economic way to do anything these days, but it's intended here only as a test vehicle to allow us to begin comparing logic analyzers. And that's the reason for all this history about how logic was analyzed in the early days. One of the logic analyzers I'll be looking at is that Rigol. This is the MSO1074Z. And of course the other, if you followed any of my other videos, you know I'm a big advocate also for the analog discovery. And as I always say in these videos, I don't have any connection with any of these companies. I'm a retired research director, and so I just play around with stuff, but I do think the analog discovery is a great tool in these environments. So let me set up to start doing some of that. Now what I've done is I have connected channel 1 of the oscilloscope to the analog input, that is the input to the analog to digital converter, and I've connected channel 2 to the output of the digital to analog converter. So this is the analog input, gets converted to 8-bit digital, then it gets latched in that 374 and fed to the output digital to analog converter where it's converted back to analog. Now if you note the output, you see that it has a little stair-step pattern to it. That is because the input frequency, or the clock frequency of the device, is right now set to 10 kilohertz. Now what I'm going to do is I'm going to raise that to 20 kilohertz, but I'd like you to be able to watch the screen as I do so, and particularly pay attention to the steps. This is 10, that's 20. Notice that when I go to 20 kilohertz, those steps largely disappear, or at least they get a lot closer together. So the speed that you operate A2D converters, of course, determines what kind of output you get, both in the digital domain and in the analog domain. So here you see we have a sine wave. What I'm going to do is now put in a square wave as the analog signal. And there you see it reproduces that pretty well. I'm also going to do a ramp signal, or triangle in this case. And once again you see that it works its way through the system pretty well. So I'm going to go back to a sine wave now, and we're going to then try to set up the MSO and later the analog discovery, because it's only when you have changing inputs that logic analyzers and similar instruments really come into their own. So let me do that now, and next I hope to have the Rigol MSO1074Z hooked up as a logic analyzer. Now I have the logic analyzer connected to the MSO. This is the Rigol 1074Z with the mixed signal option. And I'm using D0 through D8. This analyzer can do up to 16 channels, but I'm only using the first 8 channels, D0 through D7 I should have said. And up here on the screen you see I have gone back to the power supply, which is set right at 2 volts. And you see that it's hard to read this at this point, and I'll fix that in a second. But basically this shows that the analog to digital converter is switching between all ones in the lower 6 or 7 bits, and then the 8th bit is going high and low, and that's because the way that this particular A2D is set up at the present time, and I'll show you the specs on it a little bit later, it's adjusted so that it has a 2.5 volt maximum. So since there are 256 levels in 8 bits, basically it's about 10 millivolts per bit. So let me now switch back to using a square wave or a sine wave, and you'll see that once we synchronize this to the input signal, you'll be able to see how this A to D converter is working. But more importantly, I'll then be able to show you a little bit about the features of the MSO1074Z. Now I've connected channel 1 of the oscilloscope to the analog input, which is a 400 Hertz square wave at this point. And above that, you see the 8 digital channels. I'm triggering on the input, and you can see that what's causing this, the lower bit 0 and bit 1 to change is the noise on the input signal. And we can tell, since it's about 10 millivolts per bit, that we have about 30 millivolts of noise on that signal. And given the rather kludgy arrangement that I have down here, that doesn't surprise me. The power supply is that 5-volt supply there, and it's probably not very well bypassed, and I could clean all this up, but for purposes of demonstration it's actually better. What I'm going to do is vary the amplitude of the sine wave. Right now it's set at 2.4 volts max. And I'm going to lower it. You notice that it has now, this is at 2.3 volts, and the signal appears to have locked in. Actually it hasn't, but there is a small amount of noise still at the lower level. But we are now in a range in which you're getting a lock. Now, as the lower trace gets smaller in amplitude, the input to the A to D converter, which is this high level here, is going to be going down. So I'm going to go from 2.3 to 2.2 volts. I'm sorry, there's 2.2 volts. And you notice that the noise on the lowest bit comes back. Then 2.1 volts, 2 volts, 1.9, 1.8, 1.7, 1.5, skipped a digit, 1.4, 1.3, 1.2, or 1.1, 1 volt, 0.9 volts, or 900 millivolts, 800, or 700, and you notice I'm losing my trigger, so I'm going to have to readjust the trigger level. .600 millivolts, 500 millivolts. Well, I'm losing the trigger again. Rather than adjust it, you get the idea. As the amplitude of the signal goes up, the number of bits from the A to D converter goes up. Now, the reason that it's useful to have an instrument like this MSO is if you're decoding or you're analyzing a system where, for example, in this case, you have 8 bits that are contributing to the output, the analog output in this case. If one of those is wrong, either because it's being misclocked or because something is pulling it to the wrong value, it's very, very difficult to go down line by line with an oscilloscope, finding the particular bad line. It's much more intuitive and much more efficient if you can look at all the lines simultaneously, as in this case. And of course, as you get to bigger A to D conversions, like what is more the standard these days is 12 or 14 bits. There are even some 16-bit A to D converters. They're a little more expensive. But basically, being able to display 8, or in the case of this scope, up to 16 digital signals simultaneously is a big advantage. So now I'm going to use this circuit and these signals to kind of go through some of the features of the MSO1074, at least the logic analyzer part of that. Then I'm going to replace the Rigol with the analog discovery and do the same thing so that you can contrast and compare the two. Now once again, understand the Rigol, this is a 70 megahertz oscilloscope, so it has about 7 times the bandwidth of the analog discovery, which will only go to 10 megahertz. But within that first 10 megahertz, you're looking at essentially the same thing with the analog discovery that you have here on the Rigol. And I will tell you that MSOs tend to be kind of expensive, and I know that Dave Jones and others on the internet have basically opined that MSOs are not worth the money. And in all candor, with something like an analog discovery, I would say I agree with him. Because unless you're working with, say, an analog to digital converter that's operating in the 50 or so megahertz range, there really isn't a lot of advantage to adding MSO features to an otherwise very good scope and paying the high price when for less money you actually can get an analog discovery and have 2 instruments. The one downside is that here you see we are time correlated. In other words, the analog signal, which is this input, with the oscilloscope and the built-in logic analyzer, we can time correlate the analog channels of the oscilloscope with the digital channels of the logic analyzer. The box that you see down here is an early attempt at turning an oscilloscope into a logic analyzer. This is a device that was called a scope multiplexer. Particular model number is an 8001, and the way it worked is there were 8 input channels. You could control the multiplex rate here. You could select between all 8 channels or just 4 channels over here, and then the way the system would work is it would multiplex among whatever the selected number of channels was and put the output to the scope on a single channel. So, and it would do it with a DC offset. So if you use DC coupling, you would see a sequence on the screen which looked a little bit like that. Now I have to admit, it wasn't a very good solution. This particular unit still works, but I wouldn't use it. They never were really that useful. It was a good idea, but frankly they're so slow that by the time you chop up a sweep of an oscilloscope into 8 channels, there's not enough time to really do anything with any sort of decent clock rate. So that's just a little bit of history. Let's look now at how you operate the MSO. And the first thing that you need to understand is that the logic analyzer, which is this button here, takes one of the oscilloscope channels. So we'll turn off the logic analyzer and turn on all 3 channels. Now watch what happens when I turn on the logic analyzer. You see it turns off channel 4. And that's if you're using 8 bits, which is what we have up here. If you turn on 16 bits, it also turns off channel 3. After you set up the channels, and I've rearranged the channels a little bit in the interests of a little more clarity, what we have here at the bottom is the sync out from the generator. That's just to trigger. That's not a signal that's actually being inputted into the circuit. Then above that is the actual input to the A to D converter. Right now it's a sine wave. Let me change that to a square wave and you'll see what happens to the A to D converter outputs, they are basically toggling between the set of digital values that represents this amplitude and the set of digital values that represents this amplitude. Now what I'm going to do is go back to the sine wave, and you'll see that essentially what is occurring is the least significant bit is changing the fastest, and then in order the next higher bits, the bits 6 and 7, the two highest or most significant bits, aren't changing at all, and that's because I only have 400 millivolts in. I'm going to increase by 100 millivolts the input, and you see this one stays on a longer period of time. At 600 millivolts, still longer. 700 millivolts, the next to the most significant, begins to come on, because of course the issue is how long that the input stays at this level. And so the higher the input level, the more the most significant bits will be coming on. So that when you get to the full 2.5 volts input, the most significant bit will be on all the time. In fact, when you get above the midpoint, which is about 1.25 volts, and I'll tell you when I get there, that's 900 millivolts, that's a volt, 1.1 volts, 1.2 volts, and now when I go to 1.3 volts, the most significant digit should come on. And there you see it does. So this is the operation of the A to D converter. Now let's look at how you operate the logic analyzer. I'm going to reduce the amplitude so that we're not as crowded up here. And then I'm going to touch the logic analyzer button to bring up the logic analyzer menu. The current is D0. Let me zoom in, make it a little easier for you to see these. The current channel is D0, and that's shown in red. That can be any of the current digital channels. We have an on-off to turn on or off this group of channels. You may notice the D15 through D8 is off. If I turned that on, then I would not be able to use channel 3. When you turn the logic analyzer on, you lose channel 4 immediately, even if you're only using 8 bits. If you're using 16 bits, you lose channel 4 and channel 3. The wave size is the waveform size, and I'm going to go to large, and you see there 8 bits now fills the whole screen. I'll leave that for right now. You can reorder the bits. That is, if you would prefer to have D0 at the bottom, let's do that. Now you see D0 is at the bottom and the most significant, or D7, is at the top. I can set a group 1, and I'm going to set group 1 to D0, to D7. Now you notice that I'm going to change the display back to the small size. And there you see I have grouped all of them together. So now the current is not D0, it's the entire group. I just showed you how to do a group set and how to turn a group on and off. Threshold is a way to set the low level and the high level. Now there are some presets. The low level is the level below which it will interpret the signal as a 0. The high level is the level above which it will interpret a 1. There are some presets for TTL, for example. There's also CMOS, ECL, and PECL, LVDS. LVDS is, of course, the low voltage digital logic. You can also label the channels, and there are some preset labels like acknowledge, AD0, ADDR, basically address, bit, column address strobe, clock, chip select, data halt, in, interrupt, load, MISO, which of course stands for master in, slave out, and master out, slave in, NMI, which stands for non-maskable interrupt, and so on. You also can use some of the bus decode features of the oscilloscope on the digital channels. I'm not going to go into those here because if you saw my series of comparisons between this Rigol and the Siglent SDS1000, you've already seen how you do bus decodes where you can set up a parallel bus, or if, for example, this were a SPI bus or an I2C bus or whatever. So I won't go into all of that again. Now, at this point, I'm going to stop talking about the Rigol because I've shown you most of the Rigol's features, at least the ones that are most important. Eventually, I want to go over and do the same things on the analog discovery, but I think I'm going to digress for just a moment. I promised earlier in the video that I would show you how this analog to digital converter and how this digital to analog converter work. So let me do that, and then we'll come back and do the analog discovery. This is the spec sheet for the analog devices AD670 that I've been using. Let's take a look at the block diagram, and we'll talk a little bit about how this particular ADC works. Fundamentally, an analog to digital converter can operate according to several different methods, but the way this particular one works is called successive approximation. And if you've ever written code for computer code and you've done searching, you've used this technique. In computers they call it a binary search. In ADCs, they call it successive approximation. There's a register that is called the successive approximation register. You compare the input signal to the contents of the successive approximation register. In other words, within this unit is a digital to analog converter that reads the SAR and compares it to the input signal. So the way that these devices work is they split the signal space up into binary segments. So initially it sets the most significant bit of the SAR. It then compares the DAC output to the input and says, okay, am I too high or am I too low? If I'm too high, then I need to reset the most significant bit, move to the next bit, and set it. That's the next most significant bit. And so on. Each time it does that, it divides the space in half. So when it sets the MSB, it divides it this way. Let's suppose that it decides, well, it's too high. So it turns that off, and it divides that half by half and tries it again here. That time, let's say it decides that's too low. Well, it leaves that bit set, and divides the space in between again, and so on, until you get all 8 bits of the successive approximation register set to a value that the comparator tells you is the same as the input signal. At that time, it's completed. And that is the time that it takes for the ADC to compute. Now, there are other methods, for example, dual slope and other things. I'm not going to try to teach a course on analog to digital converters here. Just the fact that successive approximation is the way this one works. This D to A converter latches the input bus, the 8 bits, and then uses an 8-bit voltage switcher. Basically what is happening is this voltage switcher is putting out a voltage that is being compared to a reference, and it continually adjusts its contents until the voltage exactly matches the reference, at which time it knows that it is putting out a voltage which is exactly or at least within one least significant bit, the analog equivalent of this digital input. That is what gets placed through an output amplifier on the output. The 670 we looked at a little bit ago takes 10 microseconds to arrive at an accurate value. This will deconvert it back to an analog signal in 1 microsecond. So it's about 10 times faster. That's part of the nature of a D to A converter. There's a lot less thrashing around. Now, I mentioned earlier that there are faster A to D converters than the 670 that use better methods, but so don't assume that all A to D converters are necessarily slower than D to A converters. It just happens that this pair are. Now what I'd like to do is switch over and set up the Digilent analog discovery and perform the same demonstration that we looked at on the right. I've now set up the circuit with the analog discovery, and the way the analog discovery is connected, I'm using one of the waveform generators to generate a 20 kilohertz clock, and the other one to generate the analog input to the A to D converter. Then I'm using the logic analyzer to monitor the pins D0 through D7, that is the latched output of the A to D converter. And then I'm using the Analog Discovery's oscilloscope channel 1 to monitor the output. At the present time, the input is a sine wave at 200 Hertz. And so let's look at the Analog Discovery. Here you see at the top is the arbitrary waveform generator, and there is the analog input. Below it is the 20 kilohertz clock signal, and then below that is the oscilloscope channel 1. So that is the sine wave output, 1 volt peak to peak, that is the result of this 1 volt peak to peak input. In other words, this input is being converted to a digital 8-bit signal. That 8-bit signal is then being latched and transferred to the D to A converter, and the D to A converter is generating this output. Now over on the left is the logic analyzer. I'm triggering at the present time on DIO6, that is the digital input number 6. That's the 7th bit, which with the 1 volt input, that is the most significant digit. Remember I told you earlier that this has a 2.5 volt full-scale range, so the input has to exceed 1.5 or 1.25 volts for the most significant, which is DIO7, to change state. But nonetheless, as you see here, the most significant digit is at the top, and the second one down is the one I'm triggering on. And then below that you see the D to A inputs, which are also the latched A to D outputs. And so what this demonstrates is the use of the analog discovery to basically replace the waveform generator that I had been using and the Tektronix oscilloscope that I had been using to display waveforms, and also to replace the Rigol MSO, which I had been using to display the analog to digital outputs using its logic analyzer features. So I hope you'll enjoy watching this, and I hope it'll help you understand, if you didn't already, a little bit about how A to Ds work and D to As. As I pointed out, this was more of an exercise to create a test bed so that I could compare the MSO Rigol with the analog discovery using the logic analyzer modes. So as I say, I hope you enjoyed it, and I look forward to seeing you perhaps in a future video.